obviously, the thing that's going on now is we're still in the process, the never-ending process of taking our exams. Okay, let's quiet down. In-class part is over. We still have the computer part, the first attempt going on until tonight. Remember that because the exam is still going on, talking to people that haven't taken it yet, or discussing the exam around people who haven't taken it yet is cheating. Okay? So you have to hold back, wait for everybody to finish this first attempt on the computer portion of the exam. Then starting tonight at 8:30 after that's finished, then we'll have our second attempt available to do until Friday night. Okay, 11:59 p.m. Okay? Any questions on that? All right, so we are going to start this new material today. Because the exam is going on, we don't have any homework that's due on Monday. There are no UTF or SI things going on this week. Okay, let's quiet down, please. But we are moving on. We are really getting into the details now of what is the most important functional group that we'll talk about, right? Or group of functional groups. And those are the compounds. There's still too much talking that can contain carbonyl groups. All right, so carbon, oxygen, double bonds. So there's a whole group of functional groups. We've seen some of them so far. In fact, the last chapter we talked about was on carboxylic acids, which has one of these carbonyl groups. All right, these types of functional groups are very prominent in biology. They have lots of reactivity, and so we have a whole bunch of chapters to talk about their chemistry. Okay. The challenge will be that if we have 5 or 6 similar functional groups, to keep them all straight. Okay, because they all have some similarities, they all do some similar things, but they all do some things that are different as well. And so what we'll try to do is break it down based upon levels of reactivity and try to understand why the different functional groups will have differences they will. Okay, so if we can understand that, then it's easier to keep everything straight than, of course, just trying to memorize everything. Okay? So we're going to start into this chapter. It has a long title, Intro to Carbonyl Chemistry, Organometallic Reagents, and Oxidation and Reduction. Most of what this chapter is the reactions of carbonyl groups with strong nucleophiles. Okay, that's most of what it is. All right, so we're going to start out just by introducing some of the more of the carbonyl functional groups. We're then going to look at 2 general nucleophilic pathways. We're going to talk a little bit about why some of the carbonyl groups will go one way and some will the other way. Okay, one mechanism versus the other. We will rank the carbonyl groups by general reactivities. And then we will look at some strong nucleophiles that we're going to talk about in this chapter. Okay? All right. No clicker today since we don't have anything new. You guys are already doing plenty of questions and things already. All right, so here's the outline. So the first thing we're going to do is we're going to talk about the general structures of these functional groups, and then we're going to aim towards ranking them and looking at their general reactions. All right, so I'm going to break these carbonyl groups up into 2 different types. Okay, the text doesn't really categorize them this way, but I'll show you why, and we'll talk about the differences between them. All right, so we've already talked about carboxylic acids, right? So they have a general structure that looks like this. All right, all of our carboxylic acid, all of our carbonyl groups are essentially going to have this type of structure. I'll just put like a Y group there. Okay, so they're all going to differ on just what's attached to the carbonyl group. All right, so we've already talked about carboxylic acids. We have talked a little bit about acid halides. Right, what reaction did we do where we used acid halides? It's the Friedel-Crafts acylation. Okay, so we're going to talk more about acid halides. Really, out of the acid halides, it's the acid chlorides are really the only ones that we use. Okay, because acid fluorides are not as reactive, acid bromides are too reactive, and so the acid chlorides are in the right reactivity range to make them useful to us. All right, we've also seen some of these other groups, off and on. So the esters are like this. I'll put an R on one side and an R prime on the other side, just meaning that these alkyl groups could be different. All right, we've seen esters primarily as electron withdrawing groups, right? We saw them in the Diels-Alder reaction, right? And we probably could have them on benzene rings as deactivating groups as well. Okay? And the last one here are the amides. And so these have a nitrogen, and I'm going to put an R prime and an R double prime here. So these R groups could be alkyl, or they could be hydrogen. They could be the same, or they could be different. All right? And so all of these groups, and there's actually a couple more that we'll probably run into later, are oftentimes termed carboxylic acid derivatives. All right, and I think the main reason here is that they are all related to carboxylic acids, and I always think about them as being related by a reaction called hydrolysis. Okay, so hydrolysis is just a reaction that uses water. Hydrolysis means to cleave, so it cleaves a bond using water. All right, and so each of the carboxylic acid derivatives, if hydrolyzed, generate carboxylic acid and another piece. Okay, so let me show you how this works. All right, so we can start with the acid halide, and I'm going to draw out, let's draw a little arrow down like this, and I'm going to draw out the water molecule like this. All right, and essentially what happens is that this bond between the carbon and the chlorine gets broken, all right, and the OH will go to one side, will go to the carbonyl. Oops, come on. This OH will go here, and the H will go with the chlorine. Okay, so water molecule has been inserted into that bond. Part of it, the OH part, goes with the carbonyl. The other part goes with whatever was attached to the carbonyl, so we end up with a carboxylic acid and hydrochloric acid. Okay? We can do the same thing with these other carboxylic acid derivatives. All right, so if we draw our arrow down like this, we can draw our water molecule like this. And our hydrolysis product would here I'm going to draw the other piece first, would include the OH on this side and the H on this side. All right, so what we can see here is that an ester is essentially made up from a carboxylic acid and an alcohol, right? And in all these cases, so this is a hydrolysis reaction. We'll learn probably in the next chapter after this one that we can actually go the other way too. So we can make esters by reacting a carboxylic acid and an alcohol together. Okay? The last one here is the amide. Likewise, we can do the same thing. Add our water molecule and we get our carboxylic acid and an amine. Okay? So now these, I'm not drawing these out as reactions that we can just do just like this. All right? Because esters don't just fall apart in water, okay, which is lucky because common fats in the body, triglycerides and things like this, contain esters. But maybe it would be better if we could just add water, which we have water in our body already, and it would just cleave all the esters from our fat and our fat would just melt away. Right? That would be great. But we'd fall apart because all the membranes and everything else would dissolve. We just end up in a pool of fat and water. Amide bonds, we're also lucky, don't get cleaved just in water because all of our proteins are built up with amide bonds, linking amino acids together, right? And if these bonds just cleaved in water, then all of our proteins, all our muscle, all our catalysts, everything would just fall apart in water, okay? So we'll learn that we usually have to have some type of more harsh conditions. We either have to use a stronger nucleophile than water, or we need to add a catalyst, okay, to make these reactions take place. All right, but all of these type 1 carbonyl derivatives or compounds are related to carboxylic acids in this way by hydrolysis. 2 carbonyl compounds include the ketones and the aldehydes. So we have seen these as well. Usually as some substituent for a reaction, or we've generated both of these through things like hydration reactions of alkynes and oxidation of alcohols, right? So we've seen these as well. These are not related in the same way to carboxylic acids because we cannot hydrolyze ketones or aldehydes to give carboxylic acids. Okay, so why would that be? Why can't we, say, take an aldehyde, add water to it, even with a catalyst, and hydrolyze that bond to give a carboxylic acid? Okay, so this is the main difference between type 1 and type 2, right? So if we give this just a generic structure, and I'm going to add a Y group here. It could be our chloride, or it could be our O alkyl or ethoxy group or something for an ester. Could be the H for the aldehyde. The difference is that for type 1 carbonyl group, so the carboxylic acid derivatives, the Y group is or contains an electronegative which means that this Y group can equal a leaving group. Okay? Chloride can come off as a leaving group, right? Even an OH or an alkoxy group can. They're not great leaving groups, but they're better than a hydride or a carbanion, right? These type 2 really do not have a leaving group on them. Okay, so type 2 no leaving group. Could somebody close that door up there, or just maybe tell them to shut up or something? Yeah. Thank you. Okay, so this difference in a carbonyl group, whether it has a leaving group or not, is what dictates the different reactivities that we're going to see in this chapter. Okay? Okay, so let's remind ourselves first about just the structure of these carbonyls. We've kind of covered this already, but we know that the carbonyl carbon, and the oxygen, what's the hybridization of these two atoms? sp2, and so they're both trigonal planar. All right? So we see it drawn over here. The oxygen is trigonal planar. It has 2 non-bonding pairs of electrons, and so those are in the sp2 hybridized orbitals, and so that's what makes that part trigonal. Remember that the angles are roughly 120, right? Not only between the two groups there, but this would be roughly 120 over here as well. Remember that the double bond is made up of a sigma bond, a single bond, and a pi bond, right? That pi bond is weaker than the sigma bond, and so it's more easily broken. And so that's the bond that will be broken in these types of reactions. The reactivity of all of these carbonyl groups is really driven by the fact that there's a resonance structure here. Well, we can think about this as either resonance or an inductive effect, right? There's a difference in polarity here, and so we have resonance that puts a minus or a partial minus here on the oxygen and a partial plus on the carbon. All right? So if we react a carbonyl group with a nucleophile, all right, that nucleophile could be neutral or it could be charged. We'll see both of those situations. Which end of the carbonyl group would that nucleophile be drawn to? The carbon, right? Because a nucleophile has a buildup of electron density, right? Often has a minus charge. And so something with a minus is going to be drawn to something that has a plus. Okay, so we have a nucleophile, it's going to be drawn to the carbonyl carbon. What if we had an electrophile? This could be a Lewis acid. It could be, let's just do the simplest case here, it could be a proton. Which end of the carbonyl would the proton be drawn toward? The oxygen, right? So carbonyls can react at either end, but they're going to act on the oxygen with something that's more electrophilic, on the carbon with something that's nucleophilic. Okay? So in this chapter, we are going to look at ways. All right? And the pathways are going to differ just based upon whether this Y group can be a leaving group or not. Okay? So in all of them, they're going to have the same first step. So whatever this Z group is, it's going to be acting as a nucleophile, and it is going to be drawn to the delta plus end of the carbonyl. All right? Of course, if that comes to the carbonyl, that carbon already has a full octet, so it needs to give up some electrons if it's going to accept some. So where is it going to give them up? It's first going to give them up to the oxygen. Okay? And we could draw this as well, right? The resonance had a minus on the oxygen, plus on the carbon, so that Z group could come into the plus end and would still have the minus up on the oxygen. All right, so this is going to give us an intermediate that looks like this. With an O minus, we're going to have our Y group still on here, and our Z group like this. Right? The carbon now has 4 bonds. What's the geometry that I've drawn there around that carbon? It's sp3. What's the geometry called? Tetrahedral. So we have a very unique imaginative name. We call this a tetrahedral. Tetrahedral intermediate. All right, so it's gone from sp2 to sp3 in this intermediate. Okay, all of the reactions we're going to look at this in this chapter and in the next chapter start this way or include this step. All right, so from here, it depends on what that Y group is. So let's go up this way, and we're going to say here that Y equals a leaving group. All right? And so are these going to be the type 1 carbonyl compounds or the type 2? Type 1, right? All right? And if they're the type 1, what's going to happen is a pair of the electrons on the oxygen are going to come back down to reform the carbonyl, and that Y group is going to leave. It's going to function as a leaving group. And so then we're going to get our product that looks like this. Here, I'll put this in red. That has this Z group attached now plus Y minus. All right, so what kind of a reaction would you categorize this as? This is a substitution, right? Right, so we oftentimes call this a nucleophilic acyl substitution, because remember, this group here, without the Y, is called an acyl group. All right, so if we go back to the tetrahedral intermediate, and we go down this way, if Y is not a leaving group, okay, so these are going to be the type 2, okay, then it really can't go any further, all right? And so what we're going to do is, at that point, the reaction is essentially done. We're going to add some acid, or water can work a lot of times here. I think we'll use water or weak acid. And what's that going to do? It's just going to protonate that alkoxide, the oxygen. All right? So then we're going to end up with an H on there, and we're just going to have this Y group and this Z group still on. Okay? So what type of a reaction would we call this? This is an addition reaction. All right? It's kind of just like the addition reactions to alkenes, right? We've added an H to one side of the pi bond. We've added a Z group to the other end. We added 2 groups, and the pi bond is now gone. It's like adding HBr to an alkene. right? It's an addition reaction. All right, so these are the main two pathways. The one thing that can also happen, though, is if we do the substitution reaction up here, if the Z group that we've just added is not a leaving group either, and we add more of that Z group, then this can oftentimes react again. Okay? So the top one can do a substitution and then an addition reaction. The bottom one pathway can only do an addition reaction. Yeah, question?
Will the type 1 always go through a two-step reaction? Is it possible to do a one-step reaction, whereas the C group attaches, it just kicks the Y group?
Okay, so the question is, why do we have to draw this tetrahedral intermediate, right? Wouldn't it just be easier to just have the Z group come in and just kick the Y group straight off, right? It'd be so much easier to remember. You don't have to have a stupid intermediate to memorize, right? So what did we learn before about the likelihood of direct substitutions at sp2 hybridized centers? So if we have what we call a vinyl halide, so a bromide attached to an alkene, could we do SN2 type substitutions there? No, not really. And so what we end up having to do is go to this tetrahedral intermediate and then react from there. Yeah, so we never do a direct substitution on that sp2 hybridized atom. Okay? Yeah, question?
So what are the conditions that it would react, the top product would react again?
So the question is, what pathway would it go double? Let's just wait, and I'll show you examples in just a minute. Okay? Any other questions? Yeah.
Just to clarify on this. Oh, sorry.
That's okay. Go ahead.
So on the original substitution product, when we do an addition, is the second addition of the Y group or the Z group? Do we add a second Z or do we add Y back?
Okay, so the question is, which of these groups? So usually what we'd be doing is adding 2 of these Z groups. Okay? And really what happens from the tetrahedral intermediate depends upon whether Y or Z is a better leaving group. Right? If the Z came in with your tetrahedral intermediate, but the Z group is a better leaving group, what would happen? Z could come off, and where would it go then? It would just go back to where we started. Right? So it could go on, it could come back off. But we're only going to have a productive reaction if the Y group that's on there is actually a better leaving group than Z. That's the only way we're going to go forward. Okay? But if neither of them are a good leaving group, then the best we can do, the only thing we can do is then do the addition reaction. Okay? And essentially we have to add water or acid. This is where we call it more of a quench. So we're just going to neutralize the reaction. We're going to protonate everything that's basic in there. Okay? Just finish it off. Okay? Activities of the different carbonyls. Okay? So there's a whole bunch of these here, right? So we're going to look at 2 different factors that influence the reactivity of these groups. All right? Because these carbonyls are acting as an electrophile, they're reacting with a nucleophile, the more positive charge that's built up on the carbonyl carbon, the more delta plus, the stronger electrophile it will be, right? The more reactive it will be with a given nucleophile. So let's look first at the delta plus. Oops, come on. Okay, on the carbonyl carbon. All right, so I'm going to draw over here on the side. We have 2 kind of, let's go back to that Y group that I've been using as a generic one. we kind of have two different things that can happen here, right? We can have this Y group pull electron density away from the carbonyl carbon, right? We already have a delta plus on that carbonyl carbon. And if that group mostly pulls electron density away, is that going to make it more reactive or less reactive? Make it more reactive, right? It would build up more electron density. So I'm going to draw up here, well, I'm going to draw the resonance where I'm just going to, this is the one that I showed you before, we just have the O minus up here and a plus. And if this Y group is trying to pull electron density away from that plus, it's going to increase the reactivity. Okay? So what else could this Y group possibly do other than inductively pull electron density away? If we look at the different groups that we have over here, you know, we have oxygens, nitrogens, carbons, hydrogens, halogens. Yeah?
You could add electron density to resonance.
Right. So if there's a non-bonding pair of electrons, especially, but even an alkyl group is able to donate electron density, right? So the other possibility is that this group can donate electron density to that delta plus. And if it does that, that's essentially going to reduce the amount of delta plus. So that's going to make it less reactive. Okay, so we could draw another resonance down here. So this would be more like this, and that, oops, and let's try that again. And in this case, the Y group would be taking some of the plus charge, essentially away from the carbon. Okay, so if we're going up here, this would be more reactive. That's not very clear either, because it has more delta plus on the carbonyl carbon. Okay, this down here would be less reactive because it has less delta plus. Okay? So now let's look at our list of carbonyls, right? And look at which end of this those groups are going to be more electron withdrawing, like the top one, and which of those groups are better electron donating. Okay, which end of this do you think would be more like this? The top or the bottom? Which would be the best electron donating groups? More to the bottom. Okay? So, these groups down here, oops, you know, the ester is good at donating. The amide is good at donating. Okay? We didn't even talk about this carboxylate, and I think in the book they don't really talk so much about this, but if this group, let's say that this R can equal H or alkyl. Okay, so essentially carboxylic acids and esters have about the same reactivity as far as this goes. Okay, they both have the same oxygen attached to the carbonyl. However, if you try to react the carboxylic acid with a very strong nucleophile, what's going to happen? A very basic nucleophile. It's just going to deprotonate. It's going to go down here. Right? Is this O minus a better or worse electron donating group than OH? It would be better, right? Because this has a full minus charge. This would be a better electron donating group. So the carboxylate anion is less reactive than the carboxylic acid to a nucleophile. All right, so, okay, so the order here is essentially as I have it drawn. The delta plus on the carbonyl carbon is going to increase as we go up. Okay? So that's going to increase in reactivity. Yeah?
Just a quick question with the acid halide specifically.
Mm-hmm.
I would think that a fluorinated or a fluoro group was going to be more electronegative, so it's going to pull electron density a little harder.
Mm-hmm.
Whereas like a bromine group is going to be a better leaving group in general.
Mm-hmm.
Is there a way we can? What does the trend look like there?
Yeah, at the top here, so the acid halide. So you're exactly right. So what was suggested is that the halide is going to be, it's more electronegative, it's a better electron withdrawing group, it's going to pull electron density away. That's why it's at the top of the list, right? If we went, instead of an acid chloride, we went to an acid bromide, it actually isn't as electronegative, right? It's not going to pull electron density away as much. But what it's going to be better at is the second thing I'm going to list right here. And that is the leaving group ability, right? So we know that bromide is a better leaving group than chloride, right? It's bigger, it can better hold the minus charge. And in fact, what happens somewhat, and this goes back to the benzene rings too, is that bromide is not as good at donating as chloride. Just because it's bigger and the orbitals are at the next level out, they don't overlap as well with the orbitals on the carbon, which is only in the second row. Okay? So, as far as leaving groups go, we have chloride here. Okay? We know that these two have no leaving group. No leaving group. The aldehyde and the ketone, right? So they don't really play into this part. But at the top we have chloride, right? Then we have either OH or OR minus, hydroxide or alkoxide. Down here we have NR2 minus. Down here, what would be the leaving group for the carboxylate if we did it just like shown? It would be O2 minus. Okay? So which of these are better leaving groups? The chloride or the O2 minus? Chloride is like way better, right? So the leaving group ability also increases as we go up, but we're going to kind of loop around here because there are no leaving groups for the aldehyde and the ketone. Okay? So in general, based upon both the amount of delta plus on the carbonyl carbon and the leaving group ability, we're going to increase reactivity as we go up. Okay? Acid chlorides are the most reactive. Aldehydes would be next, but they can only do addition reactions, not substitution, because they don't have a leaving group. Ketones would be similar, right? This alkyl group is a better electron donating group than hydrogen is, right? So it's just a little bit down. And then esters and acids and amides and carboxylic, we decrease reactivity as we go down. Okay.
So even though the aldehydes and the ketones don't have leaving groups, they're still more reactive because of that?
Yes, so they are still more reactive. So the reactivity here really goes back to that first step of the mechanism. The reaction with the nucleophile to generate the tetrahedral intermediate. All of them can do that, right? And this is kind of the reactivity order for that. What they do after that depends upon whether they have a leaving group or not. All right? Any questions? All right, so let's look at the nucleophiles. All right, so the first nucleophile we're going to really talk about is hydride. All right, so remember, hydride is a hydrogen with 2 electrons, and so it has a minus charge. Okay, we've seen hydride before as a strong base, right? You can use sodium hydride to deprotonate an alkyne. Sodium hydride is also good at deprotonating alcohols. right? To make an alkoxide is a nucleophile or something. Hydride from sodium hydride doesn't usually act so well as a nucleophile, though. It's better as a base, but not a nucleophile. So we need to have some other reagents which are better at donating hydride as a nucleophile. So I'm going to show you 2 of them right now, and then as we go through, I'm going to show you 2 more which do more specialized things. Okay? So what we're going to do is we're going to look at 2 here. This is going to be sodium. Okay, here's the first reagent. This is called sodium borohydride. Okay, the other one that we're going to look at is this with a lithium and aluminum. This one is called lithium aluminum hydride. Okay. This lithium aluminum hydride, sometimes it's just abbreviated LAH. Okay, so we can think about these as hydride delivering agents if we look at the structure here. So this molecule is essentially ionic, right, between the sodium and the borohydride part, right? So this has a plus and this has a minus, okay? If we think about the BH4 part as the reaction from a Lewis acid and a Lewis base, okay? We can break it apart to a hydride plus borane, right? Remember borane from our hydroboration oxidation reaction. Okay, so this is essentially the hydride that would be delivered. Okay, so we can draw, let me draw this out again over here. So if I just have, okay, so this would be the borohydride part. So essentially what's going to happen is this is going to go like this to go down to there, right? Because boron is more electronegative, or no, is more electropositive than hydrogen is. Okay? So there's our hydride. Lithium aluminum hydride essentially functions the same. The lithium has a plus, the aluminum has a minus. Okay? We can go down here. If we just look at the aluminum part, we'd have a hydride plus aluminum hydride like this. Okay? Aluminum is directly below boron in the periodic table. Okay, so how does the electronegativity of boron and aluminum compare? Which one is more electronegative? Boron, right? Because remember the trend for electronegativity increases going up and to the right. Okay, so we're going up. So because let's do it this way, because aluminum is more electropositive, these aluminum hydrogen bonds are more polar, with more electron density on the hydrogen. Okay? Because of that, lithium aluminum hydride is very strong reducing agent, and sodium borohydride is kind of a weak hydride reducing agent, right? So this is kind of the thing we do, right, is when you learned oxidations, you had, chromium trioxide and sulfuric acid. This is our strong oxidizing agent. PCC is the weak one, right? So we just give kind of prototypes here. There's, a million, maybe not a million, but many oxidizing and reducing agents that we could use. All right, so here's hydride as a nucleophile, okay? That's what we're going to talk about first, starting tomorrow. The other types of nucleophiles we're going to look at are called organometallic reagents. All right, and there's 3 of these we're going to talk about. All of them are essentially going to have this format where we have a metal attached to the alkyl group or the benzene ring or something like that. In this case, because the metal is more electropositive, it pushes electron density back onto the carbon, and so we get a delta minus on the carbon and a delta plus on the metal. So what we're doing, we're putting electron density on the carbon, and so it makes the carbon act as a nucleophile or a base. Okay, so this alkyl group, or whatever it is going to be a strong base and a strong nucleophile. Right, so this is a way to make a carbon nucleophile. All right, we have 3 versions of this. The first is going to have a lithium. Okay, so this is called an organolithium. Okay, these are essentially acting as a carbanion. Okay, the next one looks a little bit different. Well, because it has magnesium here, but magnesium has a valence of 2, so we usually have a halogen on the magnesium. Okay, so this is an organomagnesium. And these have kind of a name after the inventor. These are called, and this is kind of a, weird word, but name. It looks like Grignard, but it's usually called Grignard. Okay, Grignard reagents. All right, and the third have 2 alkyl groups on a copper that has a lithium on it. These are organocuprates. All right. The organolithiums and the Grignard reagents are going to behave almost the same. All right? These are very strongly basic, very good nucleophiles. And so I'll oftentimes draw the reaction for one or the other, but in most cases we can use either. Okay? And then the organocuprates are much less basic, and so they're going to have kind of very special uses. Okay, so what we're going to do from here, first we're going to spend time tomorrow looking at reactions of all of these carbonyl groups with hydride. All right, these are going to be reduction reactions. And then we're going to go into the carbon nucleophiles. All right?